Now we're asked to determine whether the series, so the sum from n equals 2 to infinity of 1 over n times natural log of n converges or diverges. When we're thinking about what test to use, I think I'll start to take that approach. If you think about the tests we have available to us so far, so first we talked about geometric series, which are series of the form a times r to the n. This expression right here certainly doesn't have that form. For a geometric series, we want a constant base raised to the n. That's not what we're looking at here. Another test for convergence or divergence of series that you learned in 9.2, one of them was telescoping series. But notice that the terms here, so if we plug in n equals 2, n equals 3, n equals 4, and here I'll even write it out. So this is going to be 1 over 2 times natural log of 2 plus 1 over 3 times natural log of 3, okay, and so on. All of these terms are going to be positive. So there's no way this is a telescoping sum, because with the telescoping sum, you have positive terms and negative terms, and they all kind of collapse on themselves, and you end up with just a few terms left. So that's not going to happen here if everything's positive. Another test to consider from the last section is the nth term test for divergence. So that only applies if the limit of the terms in your series is not 0. And in this case, if we take the limit as n approaches infinity of this 1 over n natural log of n expression, that will approach 0. It's got the form 1 over infinity, so it's approaching 0, which means the nth term test does not apply. Nth term test, again, for emphasis, only applies if the limit of the terms in your series is not approaching 0. Then you can say it diverges by the nth term test. But if the terms are approaching 0, then you're not really sure. Could converge, but it could still diverge. So that leaves us with just the latest test from your notes, which is the integral test. Okay, and I'm going to get rid of this as well. So the integral test, before we should make sure that we're allowed to apply it. Remember, so with the integral test, if we turn this expression into a function of x, let's say 1 over x times natural log of x, and we're assuming here that x is greater than or equal to 2, since that's where this sum starts. This function here needs to be, so 3 criteria it has to meet: positive, continuous, and decreasing on that interval from 2 to infinity. So is it positive? Yes, if we plug in numbers 2, 3, 4, 5, and on to infinity, so this x is certainly positive, and then natural log of 2 or anything larger is always a positive number. Real quick, if you can picture your graph of y equals natural log of x, looks like this. Intercept at 1 here. So starting at 2, sure, natural log of x is positive for all x values greater than 2. So yes, this function will be positive for all x greater than or equal to 2. Is it continuous? Again, yes, because we're looking at 2 to infinity. So the natural log function is going to be some positive value here, and then x will always be positive. So we don't need to worry about the denominator being 0. We don't need to worry about the fact that natural log of x has a vertical asymptote at x equals 0, because negative values of x, x equals 0, they're not considered as part of this sum anyway. So yes, over the interval from from 2 to infinity, this function is continuous. Is it decreasing? Well, yes. So if our denominator is going to grow without bound, as x gets bigger, this x natural log of x is going to be an increasing function. Then the reciprocal, so 1 over x ln of x, will be decreasing. As the denominator gets bigger and bigger and bigger, the fraction overall is getting smaller. You know, if you have a pizza, you divide it into more and more pieces, you're getting smaller and smaller slices. So yes, this is a decreasing function. So we're allowed to apply the integral test. That means we're allowed to consider, instead of considering it as a sum of these, discrete terms, we're going to look at it as an integral from 2 to infinity of 1 over x natural log of x. And whatever this improper integral does, the series, the infinite series, will have the same behavior. So if this improper integral converges, then this series converges. And if this improper integral diverges, then this series diverges. Okay, so let's look at that. So if we take the limit as t approaches infinity of the integral from 2 to t of 1 over x ln x dx. And then I think I'm going to do some scratch work in blue here. So to actually integrate this thing, I'm going to rewrite it as 1 over natural log of x times 1 over x dx, which is equal to this. But here, you may note that this, or the 1 over x, is the derivative of the natural log of x function. So if we let u equal ln of x, then du will be 1 over x dx. So if we call this guy u, then all of this will be du. And so this will turn into the integral of 1 over u du. And so the antiderivative is the natural log of the absolute value of u, which in this case is natural log of x. So this is a little weird looking. We're going to end up with an antiderivative that is natural log of the natural log of x. That's what we get here. So this, oops, I don't want red. So back to this improper integral, this is the limit as t approaches infinity of this expression evaluated from 2 to t. And so this is the limit as t approaches infinity of the natural log of t minus the natural log of 2. And so first, this natural log of 2 business, you could punch this into the calculator. This is some finite number over here. As far as convergence or divergence, that's going to be determined by this part here, so the infinite part. As t approaches infinity, the natural log of t in here approaches infinity. And then so natural log of something that's growing without bound, that's also growing without bound. So this limit here is just increasing without bound. It's approaching infinity. Minus whatever the value of natural log of 2 is. But again, it's some finite number. And so overall, this is approaching infinity. And so again, like in the last example, the improper integral diverges. And so the verdict is that this series right here diverges. Oops, diverges.